All right, hello everybody, welcome back. Today I want to walk you through the basics of chi-squared tests, building on sort of the understanding of probability that we've been developing so far, as well as conditional probability. So with no further ado, we might as well get into it because the last time I made a lecture, I wanted to make it short and sweet, and it wasn't that short. Maybe it was sweet, hopefully it was sweet. But anyways, to start off with, let's review what kind of tests can we run and when. And this is actually normally a question again that I will ask in class, and wait for in class, and then wait for people to provide answers to before we move on. But this is sort of the most crucial information that you're going to need to get out of this class. Basically, is what should I do given data that's structured in a particular way? And so, for instance, we've talked about t-tests and ANOVAs. So you can use those when your independent variable is categorical and your dependent variable is gradient. Sorry, I'm going to clean my glasses as I walk through this. And you can contrast that with our regression analysis, which was related to what we were doing with t-tests and ANOVAs, but not quite the same thing because we could use it for cases where we have gradient independent variables and then gradient dependent variables. And what we want to learn about now is the chi-square test, as well as learn a little bit more about the proportion tests, which we can use in cases where both of these variables are categorical. And I need to line this one up a little bit better. Yeah, so part of what chi-square test will involve is just lining things up in tables, actually, so that's kind of appropriate. But this is the big change here is in our dependent variable. So before we've been looking at gradient measures like, VOT or F0, that sort of thing. Here we're going to look at categorical measures that, fit into separate, distinct boxes, basically, in a table. And so you can think of I'll walk you through a couple of examples where that will be appropriate. But for instance, it's often appropriate when you're gathering data from like perception tests where you have people picking between distinct choices, that sort of thing. That's what we're going to learn about today, chi-squared analysis. And I'm sometimes going to spell it out like this. And this is the Greek letter, which actually in the old days was pronounced he. So it's just a fancy looking curly QX, but we call it chi-squared because, we're modern day English ignoramuses. And chi-squared analysis is a way of analyzing contingency data. And contingencies are just all the events that could possibly happen within a certain framework. And a contingency table is the counts of how many times each of the contingencies actually happen in a sample. So we're going to be looking through tables that have counts of events in them, basically, to provide data for this sort of method as we go through the lecture today. Okay, so with that in mind, I want to awkwardly stick with the racial theme that I started last time and look at an example of hair and eye color in white people. And I got this example from a British textbook, or an English textbook, British English textbook. So it includes separate categories for fair and dark-haired people, which are not necessarily the terms that I would use, but coming from the U.S. But that's actually kind of worthwhile to stop and think about for a moment because we're going to put people in boxes here according to what their eye color is and what their hair color is. Eye color, I think, is maybe more categorical than hair color, but in both cases, I think there's a bit of fuzziness in the boundaries. So we're just, there may be an underlyingly gradient reality to this in terms of like how dark or fair your hair is. But we're going to stick people in specific boxes and say, okay, you've got fair hair or blonde hair, I guess, and you've got dark hair or brown hair, that sort of thing. So even if you have gradient data from whatever experiment you're collecting data for, you can sort of superimpose this tabular structure on that data if you really want to, and then you could run a chi-squared test for it. I'm kind of thinking back to that first example we looked at with linear regressions where we're correlation analysis, and we're kind of trying to look at, is there a correlation between the F1 and F2 of vowels? And, you could just plop the F1 and F2 of a particular vowel into, is it higher than the average F1 or lower than the average F1? And so, yeah, that works, or, higher than the average F2 or lower than the average F2, and they get like 4 boxes. But as was pointed out back then, when you do that, you lose some information, right? So you can use a regression analysis to maybe get some more information out of that data. But if you don't, you can still apply this chi-squared analysis to it. And the nice part of this is it's relatively easy to understand, and there are actually a lot of cases that kind of fit the clearly distinct category sort of structure, maybe a little bit better than this, but normally I think we think of hair and eye color as being pretty distinct anyway, so let's just roll with it. That's just sort of so you know. Okay, so we're going to assume a null hypothesis that hair and eye color are independent in this group of people. What we want to find out is whether or not that null hypothesis is correct or not, basically. So if the null hypothesis were true, what would the contingency table look like? And this is just going to use the principles of probability that we've talked about heretofore. So if hair and eye color are independent, then the probability of both occurring together should be the product of the probabilities of both occurring separately. So again, this is going to independent events use the product rule for their probabilities, right? Okay, maybe that's the case. So in order to find that out, we need to calculate what are the separate probabilities for people having either hair color or either eye color in this table. And so the way to figure that out is pretty straightforward. And normally I walk people through this by scribbling things on the board. Again, you can be thankful you're not going to have to read my handwriting because you can just walk through this table here. So we start out with these four numbers here. 38 people had fair hair, blue eyes, so on and so forth. We total up both rows and we total up both columns. And this data is a little bit funny because it's not evenly balanced. Normally when you would set up like a perception experiment, you'd want to have like even numbers of stimuli, that sort of thing. We don't have that here, but we can add up everything to get a total of 114 different people in this table. Whoops. And from that, we can calculate what the observed probabilities are of people having certain hair colors or certain eye colors. So for the fair-haired people, there are 49 of them right here out of 114 total. For the dark-haired people, there's 65 of them out of 114. Likewise, we can say there's 52 people with blue eyes, so the probability there is 52 out of 114. And then for brown eyes, it's 62 out of 114. Okay, so that's just the probabilities if you take them all at face value. Haha, I guess. And we'll call those our observed probabilities. And again, what we want to know is whether there's any sort of connection there. So for the expected table, we take the product of the independent probabilities and multiply them by the total number of observations, in this case 114, to get the expected value of each cell in the table. We were kind of doing this at the tail end of the previous lecture on conditional probability too, except for a different set of data. But I'll show you again how it works. So we have 114 people in this table altogether. The probability of having fair hair based on those observations is 49 out of 114. And then the probability of having blue eyes is 52 out of 114. So you just take this number times that probability, and you will get some total number representing the expected number of people with blue eyes and fair hair. You do that same thing for the brown-haired people, except in this case you change this second probability because that's the blue. Sorry, did I say brown-haired? I meant brown eyes. So this is the blue eye probability, and this is the brown eye probability. So that's the only thing that's going to change. Over here, you keep this the same. You change the hair color probability, and over here, you just change that as well for the dark-haired, brown-eyed combination. And if you crunch out all those numbers, you get a table that looks like this. So this product here equals 22.35, so on and so forth, 26.65. All the way up the scale. You don't need to know specifically what all these numbers are. You just need to know how we calculate them, and this is what we wind up with. And this, as I mentioned up here, is the expected numbers we'd get if these probabilities were independent in these two probabilities we're combining here. And we're going to compare these numbers down here at the bottom to what we saw originally in our expected or observed table here, these four numbers here. So how different are these two sets of numbers? Are they different enough for us to reject that null hypothesis and say, well, you know what, maybe hair and eye color are linked somehow in this group of people? Okay, so this is chi-squared analysis. How much does that total observed data differ from the expected data? The statistic we are going to calculate, whether you call it chi-squared or he-squared, is going to be the sum of our observed values within each cell minus the expected values within the corresponding cells. Square those differences. divide them by the expected value for those cells, and then sum up all of those ratios, basically. Yeah, I haven't sort of given you all the little subscripts and stuff here as I normally have. Instead, I'm just going to kind of walk you through the example, which again, I think it's easiest to learn this if you see how it's done. Usually on the board, but we're going to walk through it on a PowerPoint here because it's easier to read, especially since we don't have a chalkboard. All right, so for the fair-haired, blue-eyed people, we have 38 observations. We have an expected value of 22.35. If you subtract this from that, observed minus expected, you get 15.65. And if you square that, you get a value of 244.92. Okay, and then you take 244.92, you divide it by that expected value, which is 22.35. You get about 11, basically, for that number. We're going to do this for all 4 combinations. We're trying to get this number over here, and then we're going to just sum it up to get our chi-squared statistic. For the next combination, which is fair hair and brown eyes, we have 11 minus 26.65. And interestingly enough, that quantity is negative 15.65, whereas before we had a positive 15.65. So when we square that, we get the same observed minus expected squared value, 244.92. The only thing that differs here at the end is that we divide this guy by 26.65, and that's about 9, whereas this was about 11. Keep walking through, you'll notice we'll get very similar numbers here in the observed minus expected squared column. The things that differ are just the sort of specifics of how the observed and expected values differ from each other. And then also, because this number is going to change for each combination, dividing this by that will yield a different ratio or value in the tail end. So this is about 8. And then lastly, the dark-haired, brown-eyed people, we get a value of about 7. So add all those up, we get our chi-squared statistic of 35.33. Whoop-de-doo, you say, what does that mean? Well, we can actually ask R to figure out what it means for us. But before we do, we should take a moment and recognize that for the chi-squared analysis, the degrees of freedom are going to be equal to the number of rows in your table minus 1 times the number of columns in your table minus 1. And in this case, we have a 2 by 2 table, right? So like this. So 2 rows and 2 columns, 2 minus 1 times 2 minus 1 equals 1. We only have 1 degree of freedom in this guy. And our chi-squared statistic is 35.33. So we should go figure out a p-value for this chi-squared statistic. Before we do, I just wanted to show you kind of quickly what a few chi-squared distributions look like. You can plot these in R. We've done this before with normal distributions and binomial distributions and whatnot, and F distributions as well. This is the command you use. Maybe you can see that it's in the PowerPoint as well, but this is the chi-square distribution part of it. We're using this plot function again. Yeah, so just saying, take the x values, and this is the degrees of freedom. So this is the one that's going to be relevant for what we just calculated. This is a parameter here known as the non-centrality parameter. I'll tweak with that a bit as we walk through this, but basically the default value for this is 0. But if you increase it, it kind of shifts the whole thing over to the right. And this is going to plot everything from 0 to 10. So I'll just show you what it looks like. It kind of looks like one of those, well, yeah, whatever. I don't want to make too many comparisons here, but this is what the sort of default chi-square distribution looks like. And this, like I said, is the one that's relevant to what we just calculated with 1 degree of freedom. And the default chi-square test assumes a non-centrality parameter of 0. So yeah, we have a value of 35, which is like way over here. This one only goes up to 10. So we're pretty far off into the tail for this guy, so it's probably going to be significant. But be that as it may, I'll just walk you through a couple of other changes here. Maybe I'll change that. First, I'll change the degrees of freedom, and you'll see that it starts to look a little more like a skewed normal distribution, maybe with a long tail to the right. We could crank this up, I guess, maybe to 5, and maybe it looks a little bit more normal. I don't know. Yeah, so this chi-squared distribution, yeah. Just play around with this. It doesn't have like sort of one distribution shape, which is really consistent throughout. It changes a bit for the different degrees of freedom. And then I can also show you that it will change a bit for this non-centrality parameter. So this is for 3 degrees of freedom. And if we crank this up to a 1 here, it kind of gets bigger over here on the right. Yeah, and maybe if I'll even do 2 here. Yeah, it even gets fatter over here on the right. So that's what that does. But like I said, the default for your analysis is going to be a value of 0. So you can kind of focus on just this first one, which kind of really didn't look like any of the others, to be honest. It looked like this sort of parabolic. I don't want to say parabolic, but yeah, whatever this is, going from infinity in this direction to infinity in this direction and very little down here. Anyways, that's what we're working with. We just got to figure out where our chi-squared value fits into this distribution. And like I said, it's going to be way over here because it's 35. So yeah, we don't have to go, I don't even know. Does this one have tables? Yes, it does. Look at this. Yeah, so in the old days, you used to have to kind of sort through tables like this. This is a table of random digits. We don't need these anymore, even though they're kind of nice to have. But we can have R do this for us. Are there any others? Yeah, here we go. Look at this. Standard normal probabilities. This is the fun you're missing out on by taking this class in the modern day and age. But this will show you like what p-values you have for specific z-scores, right? We used to do the same thing for chi-squared tests. In the modern world, we can just run the numbers through R and get a p-value. So in this case, I'll show you kind of the slightly inefficient way of doing this. So this is our table. And maybe I'll go back to what the table originally looked like here when we first saw it. So hopefully you can see how I'm doing this, but it's got, this is the blue eyes, fair hair cell. And then this is the cell right below it for blue eyes and dark hair. And then the other 2 numbers are over here. And then I have to specify, this is in a matrix, which is basically going to turn it into like a table like we've been looking at. And it's got 2 rows. That's what that says. So when it has 2 rows, that means this is row 1 and this is row 2 before I move on to column 2, row 1, and column 2, row 2 like that. So I can hit return there. And if I do color counts, it should just plop it out in this sort of 2x2 structure that we've been playing around with up until now. If I want to run the actual test on that and find out what sort of p-value I get, it's very simple. You just put chi-square test for the matrix you're playing around with, color counts, and then it gives me the chi-squared value that it calculated, the degrees of freedom, and then a p-value, which in this case is very, very small. It's much smaller than 0.05. So yeah, there's a significant connection here between hair and eye color because this is not the big enough p-value to maintain the null hypothesis. So we reject it and say that they're dependent on each other in some fashion. We'll call it melanin. Anyways, I would also want to point out here that the chi-squared test is being run in this case with what is called Yates continuity correction. So to turn that default correction off and get the chi-squared statistic that we calculated above, you can do this, correct equals F. So that's going to be false. We're going to get rid of that, and we're going to go back to the chi-squared value we had up above, 35.3, which is more or less what we calculated there. And then our p-value is still going to be super, super small, just not quite, I guess maybe even smaller than it was in that particular case. So this one, again, is sort of a default correction it uses to sort of protect you from doing the wrong thing. And so the chi-squared value winds up being a little bit smaller than it was in our calculations. But anyways, this is where the raw numbers get you a significant connection between the two. Yeah, so that's relatively easy to do, thankfully. And I want to show you, in addition to that, how to run the same test for the poverty race data that we were playing around with last time. And in that case, we're going to need to reorganize our data somewhat. So I think we started out with data that looked like this, which I grabbed directly from one of my world almanacs, that showed the number of people of certain races in poverty in the US, and then the total number of those people. But we can't actually organize a table that way for a chi-squared test to get it to work in R, because again, we have to do this, structure our data in the form of what's called a contingency table, and that has to include counts of the various combinations of events that can happen in each cell. So for the race poverty breakdown, it therefore doesn't make sense to include the data in the total row. Instead, you have to split up the data into the number of people in each of the groups who are either in poverty or not in poverty, which you can kind of think of like, well, this is a person with blue eyes. Do they have fair hair or dark hair, right? Not do they have fair hair or are they one of the members of the group? That doesn't help in the same way. Okay, so the new breakdown will look like this. So we'll have the number of Asian people in poverty and Asian people not in poverty, so on and so forth. And then again, these are in the millions of people in the US. And I think actually breaking it down this way, where you see there's over 200 million white people in the US, that kind of may help a little make clearer like why you got that kind of weird paradox about how white people could be the least likely group of people in the US to be in poverty, but still the majority of poor people in the US are white. It's just because there's a lot of white people in this data set. So, well, there are other reasons too, but we'll set those aside for the moment. But anyways, R won't require you to calculate totals for each of these rows, but they'll come in handy for the math we'll do next. So I'll just plop the totals back down there. So I want to walk through the same sort of analysis, and again, acknowledging that with R you can do this the easy way and just run a couple of commands to get your result. But just so we know where they're coming from, if we calculate the same numbers for the chi-squared statistic that we crunched for the hair eye color data, the total number of people in the table is 343.3 million, and then the proportion or the probability of being in poverty is 53.8 divided by 343.3. So it's a probability of 15.7% or 0.157. And then everybody else is not in poverty. Again, you can think about this as another case of sort of like artificially imposing like clear categorical structure on what is essentially gradient data. But we're just saying beyond this line, you're in poverty, and above this line, you're not in poverty. But who knows what it is actually like for those people in that kind of border region. Be that as it may, everybody is either in or out. So the people who are in are at 15.7%. Everybody else is 100% minus 15.7% or 84.3%. Okay, so to calculate the numbers for our expected table, we need to multiply these two probabilities by the specific probabilities of being a member of each race. And again, we kind of did this before, but just to show you again how it works. This is the total number of people we have in the US in this census data. This is the probability of being in poverty. This is the probability of being an Asian person in the US. And you multiply those together by the total number of people, and you get 2.1 million. This is your expected number of Asian people in poverty in this data set. For black people at 6, we'll just keep on going up the scale here. Hispanic people is 7.7, and white people is 37.8. The products work out the same way. My formatting did not. So we'll fix that. And what we get out of that is the same math to calculate the chi-square statistic at the end. So we have to calculate this observed minus expected square divided by the expected value for each individual cell. Again, this is something I worked through in class, but we don't need to dwell on it too long here. But this is just Asian people in poverty. And then this value winds up being 0.076, relatively small. Black people in poverty, it winds up being 2.535. So 9.9 minus 6 is 3.9. Square that, you get almost 16, 15.21. 15.21 divided by 6 is about 2.5, right? So I'll just walk through all the numbers here. What you will notice is different here, though, is that the numbers in this column are not all the same. But the funny thing is they wind up kind of repeating themselves as we calculate the same numbers for the not in poverty people. And they're exactly the same for each racial group, kind of going up the scale here. 0.16, 15.21, 22, and 64, same way twice. Again, when you divide them by the expected numbers in those cells, you get some differences that are meaningful there. But at the end of the day, you just sum up all these numbers, you get a value of about 8.5. And there's a little bit of rounding off going on here, so it's You don't have to worry about this exactly, but it's about 8.5. That's our chi-squared statistic. And we've seen the what the chi-square distributions look like, and maybe we can revisit those again because we're going to have to change this here. This is what it looked like for 1 degree of freedom. And in this case, 8.5 would put us around here, way off in the tail again. But this was for just 1 degree of freedom. How many degrees of freedom do we have in this example? Give you a second. Right. So we have a 2x4 table here, right? So 2 rows, 4 columns. Our degrees of freedom should be the number of rows minus 1 times the number of columns minus 1. It's 2 minus 1 times 4 minus 1. It's 1 times 3, or 3 degrees of freedom. So we can take a look at that chi-square distribution again. And we get something that looks like this. So in this case, we're at 8.5, which is over here, again in the tail, not as far out, not in this extremely long tail that we saw before. So who knows? Maybe this is p less than 0.05, maybe it's not. We have to get R to tell us specifically what it thinks. But we'll go back here, and we'll see how to do this. So when you run this matrix through a chi-squared analysis in R, I'll show you how to do it. It gets a little funny for an important reason. So this is exactly what we did before. We just put everything in a big matrix called, in this case, color counts, specified that it has 2 rows. Yeah, so hopefully I'm not messing anything up here, right? So like this first column has row 1, 1.7, row 2, 11.9. And we see those first 2 rows right here. And then we just kind of go on down the scale, right? Or go on down the list. Now I can run a chi-square test on those color counts. The chi-square, like I said, the actual value one is going to wind up being a little bit different. This is with the correction by default. But we have degrees of freedom equals 3. And our p-value is really close. It's 0.0351. Turns out that's far enough out there to reject the null hypothesis. So we can say, yeah, there is a connection between race and poverty in America. But there's also this warning message that the chi-squared approximation may be incorrect. We can actually try the other way, turning off the default to see what happens there. Maybe that'll fix that error message, or maybe it won't, and in fact we'll get the exact same results. Because apparently it wasn't even applying that correction up here. It was just running the default anyways. And the reason we're coming up with this problem is because we have values in our table which are less than 5. So this is an important caveat to running a chi-square test, is that you can only run it when none of the values in the contingency table are less than 5. So this may put a damper on some of your hopes for using this for specific perception experiments, maybe. Where you can often get, values of close to 100%. In this case, we have this one number, the number of Asian people in poverty, which is only 1.7 million, but it's smaller than 5, at least the way we listed it out here. So we can fix that. I mean, so the reason it's there is because we're simplifying this a bit, right? I'm not writing out 1.7 million or 1,700,000 for this. So I could easily do that to fix it here. And in fact, I'm just going to get rid of these decimal points, and we'll say these are numbers in 100,000s, which is not normally a unit you'd use, but you could, and I will. So this is the same numbers, basically, just multiplied by a factor of 10. And then if I run the chi-squared test here, I should be okay. My chi-squared value winds up being 10 times as big as it used to be. And my p-value in that case is very much smaller than 0.05. Yeah, so, okay. This is just, a little bit of smoke and mirrors to get this to work, because it just depends on what factor you're using for your numbers in this case. But that's the moral of the message is, in a more realistic situation where you're not counting every single person in the U.S., and instead are counting like how many responses you get in a perception experiment. If you have numbers that are less than 5, you're going to run into trouble using this technique, basically. It doesn't work. It's just like the assumptions underlying the distribution no longer apply in those situations. So you'd have to do something else. I think I have a note here. If I can find it, this is the wrong PowerPoint. The alternative is using what's called Fisher's exact test, which we don't have time to go through here, but that's sort of the non-parametric alternative. And again, it just, on a realistic scale, you have to make sure you have counts of at least 5 in each of your cells before you can run a chi-squared analysis. So just keep that in mind as you go. All right. Give you one more chi-squared example, this time from the realm of linguistics, so we can get out of the more sort of politically loaded topics and do something just about fun stuff like VOT. So we'll go back to Sue's data from a long time ago where she was looking at the identification of phonation types and stops by speakers of Hindi and English. And so I'll show you kind of how to organize that in a fairly straightforward way for chi-squared analysis. Actually, maybe just to remind you, it's not the most convenient representation. So just remember we had all these different stop types with different cues. So was there voicing in the stop itself? Maybe there's a lot of voicing, maybe there's a little. And then we had different types of aspiration, like just unvoiced aspiration or maybe breathy voiced aspiration. And then people just had to decide whether in an ABX triad, the X stimulus was more like A or more like B. So I'll show you how to organize all this data. There's 4,320 lines of data in this data frame. You can convert it all into a table, which you can use for a chi-squared analysis really easily in R. You say table, contrast, correct. So we'll do this one more time. One of the fields here is whether or not they got the I keep doing this. Whether or not they got the response correct as it was, as opposed to, right. So this is what we had to filter out the incorrect responses here for our previous homework. So this is the one where they're identifying the stimulus correctly. If you want to figure out whether or not that depends on the contrast type, you just organize it like this. And you get a table that looks like this. So for the breathy versus unvoiced aspiration contrast, there's this number of correct responses and this number of incorrect responses, so on and so forth for the other 3 contrasts between aspiration types. And then if I want to run a chi-squared test on that table, it can actually do it quite simply. This is actually without making the conversion to begin with. I'm just using the variable names. I hit return for this summary command, and it tells me what the chi-squared analysis is. Basically, I get a very large chi-squared value here of 119.6. Degrees of freedom here is 2 because I have 3 rows and just 2 columns. And then the p-value is very small. So there's a connection here between the contrast type and the number of correct responses I get. Basically, is what this is telling me. I don't want to dwell on this too much, other than just say this is some handy dandy R code that you can use if you have data that's structured this way, where you just wind up having a lot of trials in a data frame like this, which have, say, a column or a field in them, which specifies whether they got a response correct or not. You can easily organize it into a table like that. A slightly more complicated way is to sort of count it out independently outside of using this table command. And then you can organize it like this, as we've done before. And we'll call this SUCounts. And that'll look like the table you just saw a second ago. And then we can run a chi-squared value or chi-squared test on that, and get basically the same result. Yeah, so this is less about the sort of linguistic situation here, which we kind of analyzed in the previous homework anyways, and more about just how to sort of organize your data in a quick and dirty manner without, again, making your mind explode. Okay, so that's basically what I'm going to say about chi-squared tests. Otherwise, I'm going to move on to proportion tests, which we've seen before in a simple version, but wind up being related to chi-squared tests in an interesting way. So before I talked about the binomial test or the sign test as a different name for it. This is basically the same thing, but in this case, I want to look at some more language data. And this is normally, past two lectures, I've kind of had little fun video clips for you to start off the lecture with. I didn't do that this time because normally at the beginning of this particular lecture, I have you guys do a little experiment and then we count up data. But can't do that virtually, so I'm just going to kind of describe the experiment to you and before we take a look at the data. So this data that we'll see will come from what's called a continuous word recognition experiment that I usually annually run for my 441 class. Some of you are in my 441 class and you may have already done this yourselves. I don't know, but either way, the way it works is there's a link for it if you want to try it. But in this experiment, you listen to a long series of words, and then some of the words are going to be repeated throughout the list. And then your decision is to decide whether, your task is to decide whether each word is old or new in the list. So like the first word you haven't heard before, so that's new. The second word might be a repeat of the first word, so you say, is that old or new? So on and so forth. Maybe the third is a repeat of either of the first two. So on and so forth as you go through the whole thing. And I will actually demo this for you right now so you can get a clear sense of what I'm talking about. So there are 40 stimuli in this experiment. Crank this up a bit so you can hear it. So number one.
Ride. Whim. Core. Whim.
Right, and hopefully you can see already number 2 and number 4 are the same word.
Whim. Core. Whim.
Right, and then we just keep on going through the list.
Mate. Boil. Hair. Rut.
And you may have already noticed there are different speakers for each word. And as you go...
Bear. Bear.
Yeah, there's another repeat, right? Every word will be repeated once, but half of the repeats will be presented in the same voice as on the original production of the word, and the other half will be presented in a different voice from the original production of the word.
Shake. Node.
Hair.
I can never
Core.
Dead.
Ride.
remember exactly when you get one of those new voice repeats.
Dead. Loathe. Rife. Rife. Fang. Bar.
Mate.
Dose.
I'm not going to walk through the rest of the stimuli, but that's kind of the moral of the experiment, is that it's easy to pick those repeats that are in the same voice, but it's usually a little trickier to get the repeats that are in a different voice. You don't remember those or recognize those as readily, basically. Yeah, so in the middle here, that's just the experiment. I've got these notes in the middle here, which again I borrowed from this Introduction to the Practice of Statistics textbook. That's why I had it out today, our old friend. And this is kind of for reference's sake, I think, more than anything else, because it shows you some of the formulas that get used to calculate the p-values for the binomial distribution. And I actually don't really want to walk you through all this right now. I'll just say they're going to be up here in the notes in case you're curious. But one of the things they kind of make clear is that there's sort of a difference between sort of the observed probability you might get out of an experimental setup like this, where you have like a certain number of successes out of a certain number of trials, and also whatever the underlying probability might be. And the contrast that gets made there is P is sort of the observed or sample probability, and then pi is the underlying probability, the population probability, I guess, is what you would say. Anyways, in this particular experimental setup, the relevant ratio to worry about is the count of successes out of the size of the sample. So focusing on those repeated words, how often do you recognize them as a repeated word, and how often do you hear those repeated words altogether? And 40 words altogether in this experiment, you get 20 repeats, and then 10 of them were in a new voice, 10 of them were in an old voice. So you just count the number of times you get a success or a hit of recognizing that that's a repeated word out of, either 10 or 20, whatever your ratio happens to be that you care about. So I'm going to just gloss through these, hand wave, and so you can look at that if you want later on, if you want to know the technical specifics. Otherwise, I'll show you how to run the relevant test for this. So the shtick with this task is that it's supposed to be easier to recognize repeated words if they're repeated in the same voice rather than a different voice. And let's see if this is the case by running a 2-sample proportion test with the word recognition data. So here's the set of numbers from this experiment that I collected from my 441 class back in 2018. So for same voice repeats, there were 9 people who did this experiment. So they got 10 trials each of these, and 88 times when they heard the same voice repetition, they recognized that it was a repeated word. But only 70 out of 90 for the different voice repetitions. So we can start off with those counts of successes for the 2 different kinds of voices or the 2 different kinds of trials. And the way you can run the test in R is maybe a little counterintuitive. So you specify a vector for the correct responses, 88 and 70, and then you identify how many stimuli were heard in both cases, so that's 90 in both cases. But now you have, these are your correct numbers, and then these are your out of numbers, basically the n in each sample. And then to run the proportion test, the 2-sample proportion test, you just put the correct numbers first and the stimuli second. So it works like that. This is a 2-sample test, so it's seeing if basically these 2 numbers are significantly different from each other, or more importantly, the 2 probabilities that they represent. So it shows you what the sample estimates are, the estimated p for each sample here, and this basically means that 88 out of 90 is this value, 0.9777, so on and so forth, and then 70 out of 90 is this value, 0.777, and you run a chi-square test for this, basically, is the way it works out. We won't work through that math again. We've done enough of that. But the p-value you wind up getting here is much smaller than 0.05. Yeah, and it's specifying there's like a 2-sided test, so on and so forth. But basically it's saying that the null hypothesis is that these probabilities for the 2 samples are the same. We're rejecting that because this p-value is so small. And in this particular case, you can say, well, the people did a lot better job of recognizing repeated words when they were repeated in the same voice as opposed to a new or different voice. Yeah, and I'll show you that if you run a chi-squared test on this in the fashion we have been running chi-squared tests in this lecture already, you get the exact same result with the exact same chi-squared value and the exact same p-value, so on and so forth. But basically this is saying there's a difference depending on the voice in which the repeated word is uttered. Yeah, so that's how you'd run the 2-sample test. I can show you some data from 2019. This is just kind of more for interest's sake. But when we last had this class, I did run the experiment in class, and then we counted up the data at the very beginning and then ran some tests on it. In this case, we split up our listeners by native language. So for the L1 speakers, they got 45 out of 50 right for the same voice repeats and 39 out of 50 right for the different voice repeats. For the L2 speakers, they had 38 out of 40 for the same voice repeats and 28 out of 40 for the different voice repeats. So it looks like a little bit of a bigger gap here for the L2 speakers. How does that translate for one of these proportion tests? Are these significant differences or not? And I'll show you a slightly different way to run this. So before I was plopping these numbers into vectors called correct and stimuli. You don't necessarily need to take that intermediate step as long as you're willing to sort of combine the data in this fashion into your proportion test command. So these are the correct numbers here, and this is the out of or total stimuli numbers here. This is for our L1 listeners. And interestingly enough, this is not a significant p-value. And, who knows, maybe if we increase the numbers here, we'd get significant result, but just with 5 listeners, we don't. So there's no difference there, even though we've seen it elsewhere. And in fact, we will see it again in these L2 listeners. So in this case, we get a p-value of less than 0.05. So for these listeners, we'd say, yeah, there is a significant difference between the number of words they can recognize in the same voice versus the number of words they recognize as repeated in a different voice. Yeah, and here's our estimated probabilities here down at the bottom. So yeah, that's just another way more about the R command than anything else. But that's how you can run a 2-sample proportion test in R. And the results are going to be kind of the same thing you get out of a relevant chi-squared test. Okay, so at this point, it would be interesting also to think about, well, we have this sort of factor of same voice, different voice in the dependent measure. And then also, same voice, different voice on, how many words you can recognize as repeated. And then we also have this potential factor of maybe listener, like there might be a difference between L1 listeners and L2 listeners. But with our apparatus so far, we don't really have a way to investigate any potential interactions between those two factors. And in order to do that, we need to learn about logistic regressions. So we're not there yet. Before we get into that topic, we also need to learn a little bit about model building through multiple regression analysis. And that will expand on what we have previously learned about linear regressions. So that's actually going to be the topic for our next lecture. And then we'll get to logistic regression right before the very end of the class or the end of the semester when we'll talk about mixed effects models, which builds on like all of this stuff that we've learned so far. So we still have a fair number of healthy and important topics to cover before the end of the semester. So stay tuned for all that. But for now, we're done with sort of our nice clean probability data and also our chi-squared test, but we're going to see them again soon. So I will look forward to seeing you all for that.